Hello everyone, this is the second video dealing with Appendix A, and we will begin talking about probability distributions. Now, we can distinguish between distributions for discrete random variables and distributions for continuous random variables. In the former case, we refer to these as mass functions. So for discrete random variable, the probability mass function is a function that assigns probability to each possible value of a given random variable. In the case of a density function, and remember this relates to continuous random variables, the probability density function is a model for the relative frequency distribution of a population of measurements. It's used to determine the probability of a random variable falling within a given range of values. So the definitions are effectively the same. And for our purposes, we are not going to put too fine a point on this distinction. In fact, very often we will just refer to probability distributions. Maybe a density function, maybe a mass function. The distinction is not that important at this point. It's just the concept that is important, which is that a probability distribution is some function that assigns probabilities to possible outcomes of a given random, or possible values of a given random variable. Alright. Now, probability distributions can be expressed in different ways. We just gave a definition of a probability distribution. On this slide, the same idea is expressed in symbols. So just looking at the discrete case at the top, you have a function f of x, which gives you the probability that the random variable x takes on some value xi. So just a note on notation over here. Usually in econometrics, when we have a capital letter for a variable, we are talking about a random variable in that instance. So in this case, x over here, capital X, is the random variable. Then when we have a lowercase letter, we are referencing a specific or a given value taken on by that random variable. So if of x over here means that we are taking some value of x as an argument, and our function is spitting out a probability that x takes on, that x, the random variable, takes on that specific value. Don't let the subscript or lack thereof confuse you. Just note that uppercase letters usually denote the random variable, whereas lowercase letters usually denote some specific value taken by that random variable. Alright, now as shown by under the properties of probability, f of xi must lie between 0 and 1. Remember, f of xi assigns probabilities to random variables. So it must lie between 0 and 1. The sum of all probabilities must equal 1. In the continuous case, we merely integrate over f of x to find between two values to find a given probability. So recall that in the continuous case, in general, you don't have point probabilities, you don't have probabilities that x takes on a specific value, but rather you have a probability that x lies within some interval between two given values, a and b. So integrate the continuous function over the range a and b to find the probability that f of x takes on a given value. And when you integrate over the entire range of the function, you end up with the value of 1. Alright. So let's use the random variable. X is the number of heads observed when we toss a coin 5 times. So this is the experiment that we've been dealing with throughout the Appendix A slides. How do we express this as a probability distribution? Well, we can simply assign to each possible outcome of X the appropriate probability. And we can just list these outcomes. So here we have the probability of that X equals 0, so we observe no heads. We know that there's only one way that that can happen, and that is if we observe only tails when flipping a coin 5 times, and therefore the probability we assign there is 1 over 32. Next, X can take on the number 1. And over here, if you look at the list of ways of observing a single head when flipping a coin 5 times, you'll notice that there are 5 ways of doing that. You can observe a head on the first flip, on the second flip, on the third, the fourth, or the fifth. And that's the only way, those 5 ways that you can observe a single head when flipping a coin 5 times. And on we go. You can observe 2 heads, 3 heads, 4 heads, or 5 heads. And this will be our probability distribution for the random variable X in this case. Assigning a probability to each possible outcome that X can take on, each possible value that X can take on. This can also be, so here we have a list, we can also express this as a table, and we can of course express this as a graph. So all these 3 things are giving us the same information. The graph, perhaps the most succinct way of doing so. This is just an example for a continuous variable. So here we're looking at height, height of an individual male in a given population. In other words, if we randomly select a male from this population, what is the probability that his height lies within a given range? And the ranges are have a 5 centimeter step in this table over here. Note that height, again, strictly speaking, not quite a random variable. However, given that we are randomly selecting an individual from a population, and we can do so repeatedly, that is then a random variable. And if we do so many times, we may observe that men shorter than 1.6 meters are quite rare, and men taller than 2.2 meters are also quite rare. And we will obtain a probability distribution that looks like this. So the cumulative density function is the probability that X takes a value equal to or less than some specified value X. Okay, probability that X, the random variable, takes on some value less than or equal to some specific value for the random variable. So this is denoted with capital F of X rather than lowercase f of X, which was the case with the probability distribution function. And here on the right hand side, instead of an equality, instead of an equal sign between capital X and small x, we have an inequality between capital X and small x. So the properties of CDFs are listed on this slide, and these are useful for calculating probabilities in certain instances, particularly property number 3 can be especially useful for calculating probabilities in some instances. This is what the CDF looks like for our example. Well, a different example here. This is the example where X is the number of the upper face when we roll a die. We know the possible outcomes. They range from numbers 1 to 6, the integers 1 to 6, and the probability for each of these is the same. It's 1 over 6. So the cumulative density function just sums the respective probabilities for each possible outcome from the lowest value to the highest value. So f of 1 is 1 over 6, f of 2 equals f of 1 plus the probability of observing the 2, which is 1 over 6, therefore we get 1 over 3, etc., etc., until the highest possible value that we can observe for x, which is 6. This would then equal probability 1. And graphically, this just looks like a step function, right? Because it's a discrete variable, we observe this step function over here. In the case of a continuous function, using the height example here again, we observe a smoother curve going from 0 probability to probability 1, the smooth S-shaped curve. And the reason for this smooth S-shaped curve is because extreme probabilities, or at least extreme values on either side of this distribution are quite rare. So we start out with very low probability of extremely short men, and as we accumulate the probabilities, as we step up in height or as we move up in height, we observe quite a steep increase in probability for moderate height or average height, and then as we as we move up to extremely tall men, we again observe a flattening of the cumulative density function here. So again, probabilities step up by much smaller, or move up by much smaller increments as we move to the extreme on the height distribution. In econometrics, we're not only interested in single variable distributions, we're also interested in two variable distributions, or what we call joint distributions. And that is a function that assigns a probability, a single value, to the probability that x takes on some specific value and y takes on some specific value. The example presented on this slide relates to a coin being flipped and a die tossed simultaneously. So if x is the upper face of the coin, y the upper face of the die, then the joint PDF, joint distribution, is given by the table in this graph. The table on this slide. Now, in instances where we have a joint PDF, that is a PDF comprising two variables, we can introduce the concept of a marginal PDF. So the marginal PDF of x is the probability that x takes on some value irrespective of the y variable, regardless of what value y takes on. And this really just then collapses back to the probability distribution of x. So f of x equals the sum over all y for the joint distribution fxy. And the same definition applies to the marginal PDF of y, except in this instance, summing over f of the summing over the joint distribution by doing so over x. So let's look at an example of this just to make it more concrete. So looking at the same table, again, x being the upper face of a coin that is flipped, y being the upper face of a die that is rolled, right? So in total, there are 12 possible outcomes. And if we want to obtain the marginal PDFs respectively of x and y, we just sum over all the possible outcomes for the opposite variable. For instance, looking at the marginal PDF of x in this case, which is the upper face of the coin, we have to sum over all possible values of y for each possible outcome of x. So x has two outcomes, heads or tails, and then we just sum each of these over all the possible values of y. So we have to sum 1 over 12 plus 1 over 12, etc., and we get to a half for head. We do the same thing with tails. 1 over 12 plus 1 over 12 is sum for the 6 values of y, and again we end up with a half. And then this is the marginal PDF of x. Again, it is simply the probability distribution of x, where x is observing the upper face of a coin. And likewise, we can do the same thing with y. In this case, we've got 6 possible outcomes of y, and so we have to sum each of these over the 2 possible outcomes of x. So for the first instance, the first possible outcome of y is observing 1. We sum the probabilities over heads and tails for x, and we obtain a value of 1 over 6, and we continue until we get to the PDF of the distribution function, technically more accurate, the mass function for y at the bottom here in red. Now, jointly distributed random variables may be dependent, they may be independent. We know that they are independent if the joint PDF of x and y can be expressed as the product of the respective PDFs for all combinations of x and y. Please note that word all, for all, italicized in this slide. So if the joint PDF for x and y can be expressed as the product of the respective PDFs for all x and y, then they are said to, then x and y are said to be independent. Conditional PDFs. A conditional PDF is a probability that x assumes a given value, given that y takes a particular value. That's the conditional PDF for x. So in this case, in the definition up here, we have f of x given y equals the joint distribution of f of x divided by the marginal distribution of y, and conversely for the conditional PDF of y. So here's an application of a conditional PDF. So here we are asked, given that x equals head, or what is the conditional probability that x equals head given that y equals 1? And to find that, we find the joint distribution of x and y for y equals 1, x equals head. So we can just read that off the table over here. So this is where y equals 1 and x equals head is given by 1 over 12. So we write that as the numerator, and we divide that by the probability, the marginal probability that y equals 1. So in this instance, we no longer look at the joint distribution, we have to look at the marginal distribution for y, and that's 1 over 6. Taking that ratio, we end up with a half. Okay, and that's where we'll end this video. In the next one, we carry on with moments.